So what are transistors? Transistors are three-terminal switches that transmit electricity in one direction. They're made from silicon, which is a semiconductor, and so it doesn't always let electricity flow through it. So it has to be doped, meaning elements such as phosphorus and arsenic have to be added to it in order to create either a surplus of electrons or a deficit. Silicon from which electrons have been extracted is called the p-type, and the silicon from which electrons have been stuffed in is called the n-type, for being positive and negative in charge respectively. A sandwich of an n layer of silicon, a p layer of silicon, an n layer of silicon is called a field effect transistor, which is widely used in microprocessors. The three slabs of silicon that are placed next to each other are the terminals, formerly called the source, the gate, and the drain. So when a positive voltage, which is an invisible field of force that attracts opposite electric charges to each other, is placed at the n gate, which is a n-type with more electrons, the extra electrons flow out of the n gate into the drain, generating an electric current. So there are millions of these transistors on microprocessors, and one could make the analogy that transistors are like neurons, and the microprocessor is like the brain of the computer. So all these transistors, they congregate to make what are called logic gates, and these logic gates use what's called Boolean algebra, something very similar to what our brain uses. An example of this is an AND gate inside microprocessors. So the AND gate is very similar in function to the logic operator AND that's common in many programming languages such as Java. So the AND gate generates current if and only if a certain number of other gates are switched on, channeling their current into this gate. If even one of the input of this collection of input of current is missing, then this AND gate will remain switched off. So in effect, the transistors become switches which either generate a current, a 1 in binary, or remain off, a 0 in binary. And immensely complicated circuits can be built by just cascading these switches. So all in all, transistors are the heart of microprocessors, providing speed and power by their sheer number and a very specialized function.
One issue we currently face in the processor industry is that they're getting to a point where they actually won't be able to shrink transistors any further. The main thing that's been sustaining Moore's law is the number of transistors on a processor. And a core has been pretty much doubling every 2 years. So once they hit this theoretical limit, it could slow things down considerably if they don't find an alternative. Once the gates in these transistors go below the size of 5 nanometers, an effect called tunneling will begin to occur. This is where an electron will be able to cross over the gate, whether the gate is open or closed, which will result in the corruption of a large amount of data. One solution currently in use to get around this is using multiple processor cores instead of a single one. This allows them to have quite a few more transistors in the processor itself without having to actually shrink the size of the transistors themselves. This, however, raises a number of new challenges for computer scientists because we now have to program them in parallel. In other words, we have to program them to execute instructions together. One of these challenges is in making sure that the two threads or instructions have the data they need to execute at the point they actually need it.